Hello everyone, my name is Kiran Purohit and I am going to present our paper, A Greedy Hierarchical Approach to Whole-Network Filter-Pruning in CNNs, which is accepted at TMLR 2024. Let us first discuss why filter pruning is important. CNNs with its millions of parameters demands huge storage and has hundreds of megabytes of memory footprint. It also requires billions of floating point operations, making it resource intensive, especially for real-time applications or deployment on devices with limited resources. Filter pruning can alleviate these burdens. By reducing the number of filters, we can cut down on storage needs, decrease the memory footprint, and significantly accelerate inference. This makes the model more efficient and practical for a wider range of applications, particularly where computational resources are limited. Network pruning is one of the fields of model compression. Given a pre-trained network, the goal of network pruning is to compress the network by removing redundant parameters, as shown in figure. There are generally two types in this field, which are weight pruning and filter pruning. Weight pruning or node pruning is a traditional way which was applied to early DNN. It checks the importance of single weight or node and prunes accordingly. Since it removes only a single node, it could not lead to practical acceleration. On the other hand, filter or channel pruning removes the entire filter or channel. These filter pruning techniques are more preferred nowadays because of their structural and practical advantages. In this study, we have also adopted filter pruning for its benefits. Two common approaches to filter pruning are uniform pruning and non-uniform pruning. Uniform pruning involves removing the same percentage of filters from each layer of the network. This method processes each layer independently and sequentially and doesn't take into account the varying importance of filters across different layers, which can lead to suboptimal performance. On the other hand, non-uniform pruning prunes different fractions of filters from each layer depending on their importance to the network's overall performance. Unlike uniform pruning, non-uniform pruning considers the network holistically with all layers working together to make the final prediction. This results in a more efficient and accurate model after pruning. Therefore, in this paper, we proposed a non-uniform pruning method. Our key contributions are we designed a faster non-uniform pruning method as different layers of filters may have different contributions to the overall network performance. We used a hierarchical scheme with two levels where the first step is to find the most appropriate filters to be pruned from each layer and the second step is to select the best layer to currently prune from. These two steps are applied iteratively for non-uniform pruning. LRF is the most closely related work to us, which is presented in III 2021. It is a channel pruning method which suggests that a filter that can be approximated by the linear combination of other filters is replaceable. In a layer, there are n independent filters. Each filter has the same dimension. Therefore, each filter can be approximated as a linear combination of other filters. Here, the lambdas are constant and epsilons are approximation error. Each lambda is determined by solving the optimization problem. Now, each filter is expressed as a linear combination of other filters and we compute the corresponding approximation error. Then LRF chooses the filter with the smallest approximation error to prune. Then the filter and its all connections are removed. For pruning beta fraction of filters in a layer, one needs to prune beta of total number of filters in that layer one by one. The network is fine-tuned after each removal of a filter. Hence, the LRF method is both slow and suboptimal. For speeding up the pruning method, we have come with an algorithm that prunes the filters of a layer for a given fraction all at once. We developed an orthogonal matching pursuit based algorithm for pruning multiple filters together. FPOMP addresses the limitations of LRF. We select retained filters in S, so the filters to be pruned are 1 to n except S. We can approximate the pruned filters in terms of retained filters. We pose a sparse approximation problem for finding S and lambda, where S is the set of selected or retained filters in a layer N is the total number of filters in that layer and beta is the pruning fraction. Let us first understand how weight compensation works. Before we start pruning, we add 1x1 convolution layer at both top and bottom as shown in the orange block in this figure. In this step, the 1x1 convolution layer have the same number of input and output channels to keep the network structure. The weight of this convolution is initialized as identity to keep the output of the original network. When we prune a filter, we modify the weight value of the 1x1 convolution layer to appropriate value. Then the loss change can be further reduced. The main problem with the FPOMP algorithm is that it selects one filter to keep at each step, which works well if we want to prune a large number of filters, but is less effective when we want to prune fewer filters. To address this, we propose FP backward, a backward elimination based approach which iteratively removes the filter that causes the minimal increase in approximation error. As illustrated, it removes one column from the weight matrix in each step, focusing on minimizing the impact of each removal. For layer selection, we proposed HBGS and HBGTS. HBGS or Hierarchical Backward Greedy Search selects the best layer to currently prune from. The key idea behind HBGS is to minimize the impact of pruning by choosing the layer that contributes the least to its layer's loss. For each layer, we compute the relative reconstruction error between the pruned and unpruned layer outputs. HBGS finds the layer where pruning caused the minimal difference between these outputs. We developed HBGTS or Hierarchical Backward Greedy Tree Search method, which aims to select the best layer to prune by evaluating the error in the output of the final layer. The key idea here is that HBGTS doesn't look at the reconstruction error of individual layers as the HBGS does, but rather it computes the error introduced at the final layer output due to pruning any layer in the network. Finally, it selects the layer to prune that introduces the minimum error to the last layer output. Coming to the results section, here we have shown the performance comparison between different pruning methods on VGG16, CFA 100 at 98% parameter reduction and ResNet 18, CFA 10 at 95% parameter reduction. We can clearly see that our methods outperform other pruning algorithms. The drop in parameters and flops is equivalent or more compared to other methods. Our methods can be used for effectively pruning large models that exceed the capacity of commodity GPUs. We use ResNet's model, which has 193 million parameters and requires 7.62 GB of GPU memory for loading. When ResNet prune to 98% parameter reduction using HBGTS-B achieves a test accuracy that matches its dense counterpart. Now we can efficiently deploy the prune model on edge devices with GPU less than 2 GB. Here we can notice that as the percentage of parameter increases, the difference in test accuracy between our proposed methods and the state-of-the-art methods also grows. At higher parameter reduction, greater than 90%, the proposed methods outperform existing methods approximately by 5%. To understand the intuition behind the filter choices for pruning using HBGTS-B, we present a visualization diagram of feature maps for two layers. Feature maps for layer 2 top row has diverse set of filter outputs, indicates its usefulness in capturing different features of the input. Therefore, our HBGTS prunes only 31.25% of its filters. On the other hand, feature maps outputs of layer 10 bottom row looks very similar, denoting its redundancy in filter outputs. Hence, 93.75% of its filters are removed by our HBGTS method. We illustrate a heat map for the relative reconstruction error and the percentage of removed filters for each layer across the pruning rounds. We observe that pruning percentage increases with each round. Relative reconstruction also decreases with pruning rounds. From heat maps, it is evident that our method selects the layer with the least relative reconstruction error for pruning. We provide a comparison of uniform pruning method in terms of pruning times. We can see that our FP backward is faster than our FP OMP by a factor of 2 for a constant pruning ratio in each layer. We also compare the pruning times of various non-uniform pruning methods. Our proposed methods HBGS, HBGSB, HBGTS and HBGTSB demonstrate superior computational efficiency compared to baseline early crop S, a non-uniform pruning method. HBGTSB is faster than HBGS by a factor of 2 in pruning time. Likewise, HBGTSB is faster than HBGTS by a factor of 2 in pruning time, hence underscoring the effectiveness of backward elimination strategy. To conclude, we proposed a hierarchical scheme with two levels for faster non-uniform pruning. FPOMP and FP backward identifies the most appropriate filters to be pruned from each layer. HBGS and HBGTS algorithm selects the best layer to currently prune from. These are the references used in the paper. Thank you for your kind attention.